Thank you, Andres. Thank you to the organizers. I'm excited to be here and to tell you about something that I think is really fun. So the idea of what I want to tell you about today is a problem or question that comes from hyperplane arrangements. And there's a combinatorial criterion for telling us a little bit of information about the complexified complement. I'll tell you what that is in a minute. And in order to actually compute this combinatorial criterion, we're going to translate this into the language of rings so we can compute Grosvenor bases and computationally check whether this criterion holds. It's going to tell us something about the topology of a complexified complement. Really rolls off the tongue. And then I'm going to show you a little bit about compute time and things like this. And then at the end, I'm going to tell you about some questions where I think these would be helpful to have answers to because it would feed us back and tell us about the topology. Okay, this is joint work with Nick Proudfoot and Graham Denham. So, let's see. Try again. Okay, so this talk has 4 parts. I'm going to try and explain the motivation to you. So this is where this topological question is coming from. In the second part, I'm going to talk about how to translate this geometric problem into an algebraic one. And then I'm going to give a brief, I'm going to sort of flash at you a little bit of the computation time to compare this more combinatorial geometric description to the algebraic one. And basically what we're going to see is doing calculations for Grosvenor bases in Macaulay 2 is faster than iterating over lists of lists of lists in Sage. Okay, and then at the end, I'm going to talk about some next steps and other things that would be good to try and understand now that we can actually compute things. Okay, so the motivation comes from the field of hyperplane arrangements. So this is a sort of active field. It's been active for a very long time. And I'm going to try and outline one of the main questions in this field. Just so we're on the same page, today when I talk about hyperplane arrangements, I'm going to talk about real hyperplane arrangements, and then I'm going to stick them into a complex space. I'm always going to start with an arrangement of hyperplanes in some Euclidean space, something that looks like R to the D. And in this case, you can think of a real hyperplane as a affine linear subspace of codimension 1. So it's the highest dimensional flat thing you can put in R to the D. I don't care about affine for this talk, so I put it in gray to indicate that I want all of my vector spaces to really pass through the origin. And I'm going to think about a collection of finitely many distinct hyperplanes. So there are arrangements where you might take infinitely many copies of each of these hyperplanes. I don't want to think about that today, partly because there's infinitely many, and partly because they're affine. Okay. These objects are interesting in their own right. There's lots of connections to other fields. In particular, many people in this room have probably encountered hyperplanes in their own work through maybe polytopes, representation theory. I said these are often the special case, the first important special cases for oriented matroids and matroids. If you think about graphs, there's always a way to write down a graph and then to orient it and describe it using a hyperplane arrangement and use that hyperplane arrangement to then tell you information about the graph. And a big question in this field is what's the topology of the complexified complement? This turns out to have many interesting and beautiful combinatorial answers, and I'll give you a taste of them today. In order to actually do that, I have to tell you what the complexified complement is. Every time you have a real vector space, you can sort of complexify it. You can either think of this as tensoring with C, or in the case of real hyperplane arrangements, hyperplanes are defined by linear equations, and you can think of evaluating those linear equations not at real numbers, but at complex numbers. So what I have here is a description. I just have a sort of more formal definition of what the complexification of a real vector space is, and then a different version of the statement that I just told you informally. And then I'm going to use the notation M of A to denote the complexified complement, which means I have my real vector space, I complexify it, I also complexify all my hyperplanes that are sitting inside this space, and I remove those complexified hyperplanes. So in the case, the case that I can draw is R, and X equals 0 is a hyperplane sitting inside R. So this is a codimension 1 space sitting inside a space of dimension 1. The complexified complement of R, the complexification of R is C, so the complexified complement of this arrangement lives in C. And it looks like this. So the point is you have one equation, x equals 0, and you want to complexify it, and it becomes z is equal to 0. So it looks like the whole complex plane, but you remove the origin. I've drawn this dashed line here to represent like the real axis. So this is sort of an image of the thing that we were thinking of as the whole, as this R here. And then, of course, there's all this extra stuff that you get from the complex plane. Questions about this? So the topology of this is quite different, right? Like, maybe I'll just point out to you that if you delete this hyperplane from this real line, you get two connected components, and they're both contractible. It's just this ray and that ray. Whereas this, when you complexify and take the complement, you have this like loop around the missing point here, and if you try and pull the loop tight, it catches on the thing. So there's some interesting topology that wasn't available in the original version. Okay. And this is a really well-studied object, and I'm not going to do it justice at all, but I just want to point out a couple of things that we already know, and then I'll sort of push, yeah.
That's a question. Can you go back to that picture for a second? Yeah. So it feels to me like I kind of get complexifying the whole space, like maybe the dimension will double or something like that. But it feels a little strange to me that the hyperplane doesn't like complexify into a hyperplane.
Oh, yeah. So what you're asking is like, why is it not this whole vertical thing, maybe?
Yeah, I guess I get it on the level of the equation, but like,
yeah.
It feels like we're talking about a different kind of a thing now than we were before. Like we don't have a collection
one could be like complex
anymore.
codimension one?
Yeah, or something.
So like, what's a good answer to this very reasonable question?
It's complex codimension one, right?
Yeah, yeah. It's complex codimension one, but you don't see it because we think in real dimensions. Yeah. Maybe that's the right way of saying it.
Okay.
Yeah. Is that sort of clear?
Yeah.
Okay. Okay. Other questions?
Is there some interesting complex function theory that describes that ring? I mean, this ring of functions that you mentioned. The cohomology that you compute, is it the cohomology of some ring of functions which somehow are singular along the...
Ooh, that's a good question. I think, you're meaning this first thing here that I haven't. Okay, so this thing should just be the cohomology ring of this space. I don't know of a good interpretation of it in terms of like a cohomology ring of functions on the space. But I'm not saying that doesn't exist, I just don't know. Yeah. Other questions? Oops, oh, shoot. Okay. So maybe let me just go through this slide. So this space, so the punchline is that we have this complexified complement. A lot is known about this complexified complement. I just want to give you the bullet points. The cohomology ring of this space is very well studied. It's called the Orlik Solomon algebra, and it turns out to depend only on the underlying matroid. So whenever you have a function, whenever you have a collection of hyperplanes that are defined by these linear forms, you can think about the dual picture. So you think of defining hyperplanes by their normal vectors. This is a collection of vectors, and it forms a matroid in the traditional sense. You look at like the linear dependence and independence among the normal vectors, and these are somehow telling you about information about the matroid. There's also a closely related space where instead of tensoring with C, you tensor with R3, and you get this thing which I've dubbed M3 of A. This thing is called the cohomology ring of that sort of like other complexified complement is the Cordoville algebra, and it has a simple presentation as well. It depends on the oriented matroid, but not the specific orientation, oddly enough. I think we're going to see both of these rings pop up tomorrow in Aya and Sarah's talks, because they're going to tell us a little bit about the cohomology rings of these spaces. Great. I want to talk today about the homotopy type. This is somewhat understood, and there are combinatorial models that are homotopy equivalent, like Salvetti's complex, but there are still many open questions. So one of the main open questions in this field is like, can I determine when the homotopy groups, like the first homotopy group is non-trivial, and then all higher homotopy groups are trivial? This is like the first question you would ask. Like, how can I draw loops in space? And how do I know that there's no higher dimensional loop sitting in my space? I want to talk a little bit about this question today, just because it's one of the fundamental questions that is open for many arrangements. Okay, I want to give you an example of just like why this is a subtle problem. So when you have a graphical arrangement, this is very well studied. In 1972, Stanley gave a theorem that says a finite graph G is from a graph, you can define a hyperplane arrangement, and then you can study this hyperplane arrangement, and you can ask what its topology is. And he says there's some characterization called supersolvable that I won't explain, but it's equivalent for graphical arrangements to being chordal. So every 4 cycle is cut by a chord. This is an equivalent condition for graphical arrangements, and a theorem of Terao almost 10 years later says that if you have a supersolvable arrangement, then the complexified complement has this nice property that the higher homotopy groups vanish. So in this particular example, we have a square, and it's cut by a chord. There are 5 hyperplanes that we could define if we were coming up with a graphical arrangement. The way you do this is you choose some arbitrary orientation of your graph. So let's say I want to have if I want to look at this thing, for each edge, I want to take a hyperplane arrangement, and I choose some orientation of that edge. Let's say I am leaving 2 and entering 1, so I would add the hyperplane x1 minus x2 is equal to 0. You can imagine that if you choose the other orientation, you get a different equation, but like the same thing is happening. So you would choose x2 minus x1. So I've added the 5 equations, 5 equations here for each of the edges. So 1, 2, 2, 3, 3, 4, this should be equal to 0, 1, 4, and 1, 3. Okay. And in this case, because it's a chordal graph, Terao and Stanley tell us that this has a particularly simple topological complexified complement. Okay. Now, if we remove that diagonal, now Stanley's theorem and Terao's theorem don't tell us that much. We know that it's not supersolvable, but it's not clear from Terao's theorem what that not supersolvable thing could mean. There's another, it's the same typo here. This should be equal to 0. Okay. So I want to sort of like, yeah? Sorry?
Or, just be clear, you're taking the complexified complement of that solution set over on the bottom right?
Yes.
Okay, cool.
Yeah. So there's sorry, I should have explained this better. Let's just show you. So I can't draw this, but maybe I'll just say it verbally. So this and this and this and this gives you a collection of like hyperplanes sitting inside R4. They have some linearity space, which is the span of the all ones vector, and then you complexify that and take that complement.
So to be precise, the complement, the complex thing is just you look at Z1 minus Z2 non-zero,
Right.
Z2 minus Z3 non-zero, etc.
Right, exactly. Yeah. Great. Other questions? Okay, good. Yeah, I hope this isn't too fast. We can, I can also slow down if we're feeling like this is too fast. Okay, good. What I want to point out here, just in case this is like a jumble of words, is that this is a very well-studied problem, and it's been well-studied for a long time. So I'm throwing up a chart here from 1986, and this is Falk and Randell. They sort of tried to encapsulate a bunch of different arrangements, or different properties of arrangements that you might have, and checking their relationship to this k-pi1 property. They did update this chart in 1998, but their update isn't as like visually striking. So I just want to show you, so here we have I don't know if it's legible, but we can have supersolvable here. So supersolvable implies k-pi1, that's listed as true. And you might ask, is the converse to Terao's theorem true? So k-pi1 and supersolvable, that turns out to be false. So that converse to the theorem that we just saw, at least here it's listed as false. Okay. What's also striking about this chart is that there's 2 meanings of question marks. It might be hard to read, but there's like single question marks and double question marks. The single question marks mean that it's not known. Double question marks mean it's not known, and it's very interesting. we are kind of in this double question mark here. We're going to talk about this today. So this is the relationship between k pi 1 and com, which means combinatorial. So I want to understand if there's like a combinatorial criterion that can tell me if something is k pi 1. It's a double question mark since 1986. Okay. This is still a very active area of research. It's not that like people forgot about it. So they had this update in 1998, but I'm going to talk about some stuff that came out last year as part of what I'm going to talk about today. And then, I mean, as I was writing this talk, another paper came out on the archive where someone had found a new family of arrangements, and they were classifying when they were free and factored and supersolvable and these kinds of things. So they were trying to understand which arrangements satisfy these properties or not. Great. So in this talk, I want to give some kind of combinatorial criterion to test if your complexified complement fails to be k pi 1. So we had all these forward implications, and now we're trying to get some backwards. Okay. Great. So now I've now sort of talked to you a little bit about how to go from this geometric problem to an algebraic problem. Okay. So just sort of to orient ourselves in the conversation, there's a bunch of properties, and people are interested in, actually, maybe I'll just point this out here. So there's a bunch of properties here, like supersolvable, factored, free, fibered, lower central series, rational k pi 1, parallel, formal, simple. These are all ways where people are trying to come up with combinatorial or other sort of checks for this property here. And this is, people have tried many things, and they haven't always been successful. But many of them sort of go the direction, if it has this, they're stronger than k pi 1. So they're like supersolvable implies k pi 1, but then the converse would be false.
So you don't say test whether it's k pi 1. Is this a one-sided criterion that sometimes works?
Yes. This is the problem. So yeah, this text here. So last year, Yoshinaga introduced a new criterion. If you are k pi 1, then you have Yoshinaga's criterion, but the converse is false. There are a couple of counterexamples to this. The fastest way to get a counterexample, or the simplest, I think, is using some of the results that I'll tell you a little bit later. But yeah, so this is not equivalent to k pi 1, unfortunately. Although, like, if there was a condition that if you could repair Yoshinaga's criterion and get an if and only if, I think this would be like pretty awesome. And this would like solve that double question mark question from before. Okay. So the downside to Yoshinaga's criterion is rather difficult to compute by hand, except on small examples. I'll show you a small example, and I'll sort of tell you why it doesn't scale so well. And what I want to sort of convince you in this talk is that Yoshinaga's criterion is actually an algebraic condition, and we can use algebra to better compute this criterion and see whether it passes or not. Okay, good. Questions? In order to tell you how Yoshinaga's criterion works, I don't like this slide. I promise you I will explain it in words. I have to sort of indoctrinate you a little bit into the language of oriented matroids. So the idea is that, this is a typo, this should just be D. The idea is that when you have a hyperplane arrangement, you have all these half spaces that come with it. So let's do an example. Can people in the back see the little red arrows? Okay, great. So when you have a hyperplane arrangement and you make some choice of the functions defining each of the hyperplanes, you're choosing an orientation. So when we chose when we took this graph and we oriented the edge like 1 to 2, we chose x1 minus x2 instead of x2 minus x1. Somehow you're implicitly deciding that each hyperplane has like a positive and a negative side, which is just you change the equality to a less than or a greater than. And so what I've drawn in this picture, sometimes this is called a hyperplane arrangement with a co-orientation, but I'm just going to call it an orientation. And the idea is that I've drawn little red arrows pointing into the positive half space. And somehow when you're trying to understand hyperplane arrangements, it sometimes becomes easier to talk about the intersections by denoting like which side of the hyperplanes you're on. So for example, this pizza wedge here is on the positive side of H1 and the positive side of H2 and the positive side of H3. And this ray here is on the positive side of H1 and on the positive side of H3, but it's actually like sitting inside H2. So when I'm talking about a signed set, I'm trying to use some shorthand to describe these intersections. So for example, like this thing, this ray here, I might want to describe in the language of it's the positive side of 1 and 2, and it's not on the negative side of anything. So when I'm talking about, yeah?
What is E? S subset of E?
Scanning.
Second bullet point.
Second bullet point, okay. Let's find it. Okay, this thing. Yeah, right. It's this thing. It's gonna be this in a minute. Yeah. I really don't like this slide. I tried to make it as compressed as possible. I'm so sorry. It's unreadable. This S is your ground set. I'm using E there because I thought, in this case, it's 1, 2, 3. Okay. So the point is that these signed subsets are somehow telling you about the ways to intersect half spaces, and that's kind of what we want to check. So this K-consistent criterion, what it's saying is that, so this particular plus 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 vector, if you intersect all those hyperplanes, you get something non-empty. But if you're looking at there's only 6 chambers here, and 2 to the 3 is 8, so there's 2 sequences of pluses and minuses that theoretically should never appear. So if you try and intersect those half spaces, they're going to be empty in this case. So you can think of taking plus, plus, minus, and you would take the intersection of H1, the intersection of H2, and then the wrong side of H3, and there's no open, like if you think of these as open half spaces, that thing is empty. But if you look at any subset of the indices, so if you look at these two, or these two, or these two, the intersection is non-empty. And so this K-consistent condition is saying, I take some signed subset, and I check on all K plus 1 subsets whether that intersection is empty. So it's weaker than being a tope or a chamber. Okay, where did it's over here. I'm losing this thing. So geometrically, the signed subset story, like the K-consistent is this notion that like you maybe don't get to, you have some sequence of pluses and minuses and zeros, and you check on all K plus 1 subsets whether it's empty or not. And if it's not empty, we're good. Okay. That's probably the most technical part of this. I say that big sigma is the collection of all K-consistent signed sets, and then little sigma is the number of those things. And Yoshinaga, I say that your arrangement is Yoshinaga of rank K if your little sigma of K is equal to little sigma of R, where R is like the size of the largest circuit of the arrangement. So what I mean is, at some point, sigma R doesn't keep changing. So you like sort of go, if you can check, in this case, if you check all 3 positions, you are always going to just determine the number of chambers of the arrangement. So if you check them all simultaneously. What this means, and if you keep going, and if you check like 4 positions and 5 positions and 6 positions, like there's like you're just checking 3 again. So there's some point where there's some R where R stabilizes and it doesn't get smaller anymore. You're not kicking out new things. And then if you've got something that's lower than that smallest thing, but it's already equal to the stabilized number, that is sort of the interesting part of Yoshinaga. Yeah.
So sorry, I think I missed what.
Yeah.
So the K is like the number of non-zero positions.
No. the K, sorry, no, this is a good question. Sorry, yeah, it's a bit hard to explain. The point is, if you have, the K is telling you, you look at, so you take you have these like orientations of all the hyperplanes. So you have let's have this one has no zeros in it. I want to check every subset of, let's say, 2 of these guys. And if I look at every subset of 2 of those guys, or 1, I want to know if that's empty or not. And if every 2 subset or 1 subset has a non-empty, the corresponding intersection is non-empty, then that thing is 1 consistent. It is off by 1 in the indexing.
So like the other positions can be anything?
So it's there's like a for all condition here. Maybe I'll try and do a bigger example. Is that going to help?
That's all right. That's all right. Sorry, I
Yeah.
don't want to derail you.
I just want to say, like, for this one, if I wanted to check this for k is equal to 1, I would check, you would have to check, like, at position 1, if h plus is not empty, and then you would have to check if, like, h2 plus is not empty, and then you would have to check if h3 minus is not empty. But if you wanted to do this, and then you would do this for the 2, so it's k and then 1 bigger as well. So you would also have to check if h1 plus intersect h2 plus is non-empty. And then you would have to check if h1 and h3 are non-empty. Yeah. There's many things to check. But you can already see why this is like computing this the number of k-consistent covectors is difficult, because you would like produce all 2 to the number of hyperplanes things, and then you would sort of check this funny condition over all subsets. And Yoshinaga, basically what he did is he could show that the number of k-consistent covectors has to do with the homotopy groups of the complexified complement. So if you have, what he shows is if you have a real arrangement and its complexified complement satisfies this k pi 1 property, then you have this condition for k is equal to 2. So you would be checking subsets of size 3 or more. Or less, sorry less. Okay. This is difficult to compute by hand because it involves lots of iterations of lists over lists. Okay, I want to show you an example, which is just for this graphical arrangement, and we can see it being used to get some converse to something we couldn't come up with before. So for graphical arrangements, there's some dual version where I'm just sort of understanding orientations and trying to figure out if I can come with oriented cycles. So in this case, I'm just checking that, so in this case with the square with the diagonal, I'm sort of checking that anytime I were to orient this square so that I can walk around and never walk a bad direction of the square, anytime you do that, you're actually orienting one of these 3 there's no orientation of this third edge, there's this last edge that like allows you to not also orient the triangles. So it's somehow about like gluing together the orientations of these chords in there. And so Yoshinaga's criterion holds. It tells us that this arrangement could be k pi 1. On the other hand, this arrangement, you can just check sigma 2, so you can orient this guy any way you want, and you'll never produce a 3 cycle that's like oriented so you can walk around it without going backwards on an edge. So there's 2 to the 4, there's 16 different orientations of this that don't cause issues for a 3 cycle. But when you go up to sigma 3, you're now looking at 4 and smaller cycles, and the problem is you have 2 orientations of this cycle that you could choose that allow you to like drive forward and back without going backwards along an edge. So sigma 2 is 16, sigma 3 is 14. Since those numbers are different, they're sort of always decreasing, it tells that this graphical arrangement does not satisfy Yoshinaga's condition and can't be k pi 1. Yeah.
It's just kind of like a weaker version of the super stability.
Super solvability. Oh yeah, sorry.
Super solvability you mentioned earlier.
You should, yes. This is, or let's say this, in the graphical case, this is exactly what you should be thinking about.
Is failure hereditary on your data in a way that gives you a simplicial complex or monomial idea?
Sorry, one more time?
Is failure hereditary on your data as you move to different sets in such a way that gives you a simplicial complex or a monomial ideal?
What do you, sorry, I don't understand.
Well, you're comparing lots of different situations and saying yes, no.
Oh,
Sometimes that gives you a simplicial complex.
Oh, you're saying like if I have a graph, let me rephrase the question and make sure I'm understanding it. So you're saying like I would take like the collection of all, so this is just for graphical arrangements. You're saying like for
Well, you kept giving us examples and
Yeah.
saying yes, and other examples and saying no.
yes,
Do they form a simplicial complex?
the collection of all ones that say like all arrangements that say like all arrangements that are Yoshinaga, do those form a simplicial complex?
Or the other way around,
Or
I
the
didn't
other way,
follow it well enough to guess which way.
That is a great question. I'm not sure. Yeah, presumably not. You would have to determine the relations, but like this, well, let me just say one thing. So the relationship between the arrangement from this and the arrangement of that is that you delete one hyperplane. So this is a hyperplane arrangement that's contained in this one. It's like a subarrangement. And this fails Yoshinaga's test, but this one doesn't. So I don't exactly know what the simplicial complex structure would be, but if it's like containment of arrangements, containment of arrangements doesn't necessarily preserve Yoshinaga's property. Okay, yeah. Okay, great. I think I was parsing the use of the word hereditary. Okay, great. Those of you guys who've seen this before, maybe this is familiar. This description in terms of half spaces and intersections being empty and non-empty is very similar to the description of the Varchenko-Gelfand ring, which is a ring that is independently interesting. It showed up as this cohomology ring of the R3ified complement, but now it turns out, or sorry, its associated graded showed up as the cohomology ring of the M3 version. But it's like if you took these sign dependence things, so this is, I'm looking at these signed sets, but now I want the intersection to be empty. So this would be an example of a signed dependence in this case because the intersection of everything is empty. I don't require that there are no zeros in this dependence definition, but this example is so small that that's what's happening. If I add another hyperplane here, maybe I could get signed dependences that had a zero. And the Varchenko-Gelfand ring is just a ring version of that. So the origin of this ring is you start with all the chambers of your arrangement. You take Q to the chambers, and you multiply things pointwise. So you can think of if you had 1 on this chamber and 1, 1, 1 here, and you multiplied them, you would get the zero everywhere function. And this ring has like a beautiful description in terms of Heaviside functions defined by the hyperplane arrangement. So there's one variable for each of the hyperplanes of the arrangement. And this is like sort of like non-trivial, it's not immediately obvious to see this, but it is true that these things correspond to these Heaviside functions. Of course, they satisfy certain relations that come from the geometry of multiplying things pointwise. So when I say Heaviside function, I mean like 1 on this side and 0 on this side. And so, like for example, maybe I want to take 1 on one side and then 0 and minus 1. So this side, it's 1 here, and then I multiply it by its negative, and pointwise, these things are 0. So this gives rise to this relation that's just saying like the two half spaces are disjoint. These dependence relations have a similar structure, and they come from understanding, like just multiplying these Heaviside functions together and checking the relationships that they have with each other. But what I sort of want to show you is that to translate Yoshinaga's criterion into an algebraic setting, the Varchenko-Gelfand ring is somehow the right place to do it. And we can prove this mathematically, that if Yoshinaga's criterion holds for rank k, then the Varchenko-Gelfand ideal is generated by those Heaviside relations. So the opposite sides are opposite, or if you multiply two opposite like disjoint half spaces, that's 0, plus the dependence relations coming from dependencies of size k plus 1 or less. This, for those of you who are experts, this is not a Cordoville statement. If you take the naive statement for the Cordoville relations, they're not always the same. So just as a warning, this is a filtered ring. and this is a graded ring because you take the top degree components. But the statement doesn't work there. You need like a different generating set. So the upshot of this whole machinery is that instead of doing exhaustive searches on sets and sets and sets, we can plug this relatively uncomplicated ideal into Macaulay 2 and do calculations. Okay, good. Just checking the time. Great. Oh. Okay, let's come over here. Okay. I will just show you, like, just to give you a sense of what this means. We already know that Yoshinaga's criterion is going to fail for this guy because we did this calculation. But we can also check that there just aren't any dependence relations. Like this is translated into the ring language, is that there aren't any dependence relations when you're looking at dependencies coming from things of size 3 or less. So you know already that there's going to be a dependence relation when you start looking at this cycle. Like there's a cycle here, there's no 3 cycles, so you will have no dependence relations, and that you get dependence relations for the first time at like sigma 3. Okay, and so it already tells you that these things are not equal, so Yoshinaga fails at rank 2. It's a little bit more complicated to say the same statement for this guy, but the idea is that on the level of rings, you come up with your dependence relations and you just look at them and you can check that like the 2 triangles, if you look at the ideal generated by the cycles coming from these 2 triangles, you can glue them together to get the big square. Just like on the level of ideals, this is a calculation about like multiplying things together in the right way. I sort of like explained it here in words, but so the idea is just that we can do calculations in the ring, and it's not that hard. Okay. So I want to tell you a little bit about like computationally. This is a computational workshop, so I want to show you a little bit about like computationally what this does for us. So I think it's easy to see that there's a lot of stuff to calculate here, but this also makes a time difference in the way that we compute things. So I want to also point out, like, why is it useful to us to have fast run times? And the short answer is, like, we would like to make good conjectures. This is like a difficult problem, and many people have worked on it. And there's like a couple of things that we might want to do. So in particular, there's an arrangement, the type B reflection arrangement, and its subarrangements turn out to give rise to counterexamples to certain conjectures. And there's been a lot of work sort of classifying which of those subarrangements of the type B reflection arrangement are k-pi1, but the converse is basically untapped. So like you can say, if the graph has this property, then it is k-pi1, but it's like the converses are all missing. So what we sort of aimed to do with this project was to choose like a concrete characterization problem and help us complete this characterization. And that's sort of like, in order to conjecture what the backwards characterization should be, we want to just compute lots of examples and see what was going on. So in order to do that, we wrote some code, and we wanted to write code that was fast enough for us to run on the Texas A&M compute cluster, Whistler. It's a joke. Do you guys know the Blade series? Like the character? Okay, great. There's a Marvel superhero called Blade. And blades are the things that you have for when you're doing like when you're doing one of these compute clusters. There's like blades that are like the different pieces you put in there. And Whistler is like the guy at home in the Marvel universe who's watching over Blade. Okay. But with the naive implementation, with the implementation that like we get from Yoshinaga, this calculation would have taken a really long time, and it's significantly faster in Macaulay 2 with Grosvenor bases. Just to give you a sense of this, so I implemented it once, I called it naive implementation, and I used a slightly different version of Yoshinaga's criterion that's a little faster than the one I showed you. It has to do with intersections of the hyperplanes, or flats, but I won't go into it because it would take a lot of time to explain. But then the other version is using rings. So I sort of implemented both of them and then ran both of them.
How do you parallelize for a cluster?
That's, oh yeah, okay. So I promised you parallelization in the abstract. So this was kind of a lame version of parallelization. I've done like more sophisticated ones. In this case, we were only checking subarrangements of type B. So what I ended up doing, which I think is kind of lame, is I just had like multiple nodes set up running the same calculation. So like
It's called embarrassingly parallel and nothing embarrassing.
yeah. So it was like, the
It's not lame.
great.
Yeah, right, it's not lame.
Yes.
Okay, great. But yeah, so like because you have a fixed set of nodes, you can just say like I want all graphs on nodes this size, all graphs on nodes on this size, and all graphs on nodes this size, and then just check it. Okay, great. Also a quick shout out, there's a hyperplane arrangements package. I am not the author, but I used some of the stuff they wrote, and it was really helpful. They don't have the Varchenko-Gelfand ring, but it's not so hard to implement, that's it. Okay. And I just want to give you a sense. So here's the timing for these two. So I implemented, so here's the Sage computation, and here's the Macaulay 2 computation. The reason this is I2 is because I loaded the file first. But this took a couple minutes, this took a few seconds. And this is the braid arrangement on 6, or of rank 5, or on 6 nodes. And you can already see that this is much faster. And then the Macaulay 2 calculation also scales pretty well. So if you do the next ranks, it's also a couple of seconds. Okay. So the ring calculations are like significantly faster. One of the things that was asked for in the description was like, where do we go from here? So I wanted to tell you like some of the successes we've had with this project and some of the things that I think are open and would be helpful to solve in order to push the whole kpi1 problem forward. So first I want to talk about some successes. So this was like pretty fast to compute things. It's cool because it's a use of the Varchenko-Gelfand ring to compute things that are not a priori like related to M3A, which I thought was pretty cool. Aya and Sarah are going to talk about more about this. I mentioned this earlier. They're going to talk about more tomorrow morning, but not in the context of homotopy groups. I think they're going to talk about like representation theory aspects. We can also prove sort of new things with this. So there was a question in the back about, is this similar to a beefier version of supersolvability? And the answer is, it's because supersolvability for graphical arrangements is equivalent to being chordal. And you can show that whenever you have a chordal-oriented matroid for some correct notion of chordal that looks like what it sounds like, chordal implies Yoshinaga's criterion. So that's what the connection is. And then in the case of these type B reflection arrangements, which include all graphical arrangements, braid arrangements, threshold arrangements, many things that we know and love, you can get more precise statements about these characterizations because we know what the circuits look like and we can say more concrete things about the dependent sets. Okay. So that's the successes so far, but there's still a lot of loose threads. A lot of them have to do with like actually computing things. So the biggest question is like, can you upgrade Yoshinaga's criterion to get an equivalence condition? Like, we know that it goes one direction, can you make it equivalent? But then there's like sort of two other things that are maybe worth pursuing, which is one, can you use symmetry of the arrangement to exploit that to even improve the calculation? So if you know that like all the dependence relations, if once you compute the dependence relations of this piece here, you just act on them by some friendly group, and you can get all the dependence relations everywhere, maybe you can actually make this even faster than it is and compute higher information about these things. This is probably the most interesting as a starter case for graphical arrangements that are not chordal for the reason we just talked about. And then the other question is, are there, just more generally, like, are there interesting families of arrangements where you can conclude whether Yoshinaga's criterion holds or not? This is interesting for ranks higher than 2 because even that tells you about some topology of this complexified complement. It has to do with like the dimensions in which you can embed certain spheres. Okay, so those are sort of 3 loose threads. There's of course many more because this is relatively new, but I think that's what I wanted to talk about today. So thank you for listening.